Dear colleagues, we want to display a method how to gain an energetic benefit from the load change of an hydraulic circuit, where one or more pumps are operating and for any reason the user is changing the head requirement. Actually, to get the benefit, we should change the pump. But what does it mean? Either to modify the drive, or to replace the motor, or to change the pump itself. But all of them are expensive methods. And here I want to show you another solution, cheaper, quicker, and even more effective. Let's see together. The problem is that one. We have a circuit, for example a heating loop, where the exchangers are connected in series. The pressure drop is known 30 meters, and the pump is supplying a certain amount of water. For a technical reason, we change the components so that the circuit is different. Let's say we join the two exchangers in parallel now. The head loss of the loop drops into 20 meters. If we keep the same pump, we won't get any saving. Let's see afterwards. We need actually another pump, smaller, or to retrofit a variable frequency drive. Reason why the circuit change is not having an automatic effect of energy saving is displayed here. This chart is general and valid for any circuit. The red curve is the head curve of the pump, and the green curve is the curve of the load before the change. The orange is the load after the change. Actually, the working point is moving onto the pump curve to the right, and the system head actually drops, but the flow increases. The power may not decrease, but depending upon the pump performance, can even increase. That's because normally the flow increases more than the decrease in head. Besides changing the pump and adding a frequency drive, we have another way to proceed. It consists of trimming the impeller into a smaller diameter. We need to remember here the affinity laws, saying a relationship between flow and head versus diameter. Definitely, if you reduce the impeller diameter from D1 to D2, the flow reduces proportionally, and the head reduces with square law. We need to trim just the blades and not the disc where the blades are welded, the structural part of the impeller, and that to avoid volumetric losses between the impeller and the casing and also cavitational problem. The effect of such a change is same as by using a frequency drive, but we avoid the drive losses. Of course, we can adopt it only if a constant speed is required. Let's see now in detail how to proceed. We start always from the operating conditions before the trimming. The pump is working with a defined head and flow that is at the intersection between its curve and the load curve. For this condition, we can also estimate the power demand. Now we get from the pump curve the head at no flow, H0, so that we can write an analytical approximation formula for it, H0 minus alpha times Q square. It is a parabola. By plugging in the values of Q1 and H1, we get the value of alpha. That is a sort of curve shape. After the trimming, head and flow are changing as per the affinity law. H2 is H1 over beta, and Q2 is Q1 over square root of beta, being beta the ratio of the diameters square. Important to the mark is that the found values Q2 and H2 are still sitting on the old load curve. The new operating point is sitting on the intersection between the new pump curve and the new load curve instead. And to find the new pump curve, we need the static head. Let's call it H0 prime. If we assume the shape of the curve does not change, alpha stays therefore the same, and by plugging the found values of H2 and Q2 in the formula of the new pump curve, we get the expression of H0 prime equals
the old H0 divided by beta. Let's find now the new head H3 corresponding to the old flow Q1. That is equal to H1 minus H0 times beta minus 1 over beta. And this point is actually sitting on the intersection between the new pump curve and the new load curve. And the new power is given by the product of the new head H3, the same flow Q1, divided by pump efficiency eta. The formula we have found gives the new head H3 as function of the trimming ratio beta, but actually we need the inverse formula. We need to find the trimming diameter or the trimming ratio by knowing the new operating head at same flow. Who tells us the head? Only the process can, and the process curve we have to know first. For a closed loop, it has a simple expression. H equals K times square Q. The constant K we can find by knowing one operating condition. If the process changes, it changes the constant K into the new value K prime. We assume K prime less than K, otherwise the trimming procedure won't find application. Should be K prime known, then H3 is also known from the previous H1 by means of this simple relation. Now we invert the formula found at the previous slide and we get beta equals to H0 divided H0 minus H1 plus H3. And if we want the expression as function of the diameter, then we have the formula in red below. This is an example of a real circuit. The delta P, or head, is changing from 30 to 20 meters, and the pump data are also known. Q1 is 140 cubic meter per hour, the impeller diameter 162 millimeter, and the metered power 15 kilowatt. The pump curve is also given. Now we need to say how much has the impeller to be trimmed, or in other words, which is the diameter of the trimmed impeller. Moreover, what will be the expected power? The static head of the pump is displayed in the head curve side, and since in this case the curve is not really a parabola, at least not a parabola with a vertex over h-axis, we need to assume the peak value here for H0, that is about 35 meters. The starting value of the head H1 is 30 meters, the target H3 is 20 meters, and the starting diameter is 162 millimeters. We have all the ingredients, and from the formula we find for the trimmed diameter 137 millimeters. The expression of the power is head times flow divided 360, that is a conversion factor, and divided by the pump efficiency. But who tells us the efficiency? We assume it will not change from the original condition. We may get it from the power expression before trimming. So, using the same formula but inverse, we find eta 77%. And then the new power after trimming is 10.1 kilowatt. If we compare with the real curve, we find 10.2, very close. The trim diameter, the real one, is actually 141 mm instead, so we have a bigger deviation of about few millimeters. And the reason stays in the approximation, because the pump parabola is actually shifted about 50 cubic meter per hour on the right side. So this will be the vertex of the curve, and therefore a more precise curve function should have been used. In many cases, we don't need to run the calculation as displayed because they are available from vendors, the charts of pump performance versus impeller size, like the one displayed here. That makes the selection quicker. However, it is always recommended to run a preliminary investigation by means of the formula we have learned right now, that is not difficult by the way, to assess its feasibility and then make fine-tuning by means of the chart.
In this lecture, we have learned an important concept. In a water circuit, does not exist energy saved for free. If we clean an exchanger or increase pipe diameter, that do reduce pressure losses, but does not reduce the power spent by the pump, unless we take a corrective action. And the actions are three: change the pump, use a frequency drive, or trim the impeller. And the last one is the simplest, the quickest, and the most economical. Therefore, we must be aware of that. See you again.